Well, good morning, everyone. So Matthias last night was out having a cigarette, which he shouldn't have been doing, of course, and he spotted something happening in the heavens. And in the heavens, somebody knew that there was an Institute of Physics meeting today, and a fireball came tumbling across the skies of Ireland and the UK. And it was a really striking fireball, and it broke into about eight pieces. Now, Matthias lives in a built-up suburban area and was able to see this. I think it was about 11 o'clock last night, and this is what I picked up this morning on Sky News. So a nice kick-off to the beginning of the meeting. So that sets up what I'm going to talk about today, something else celestial. I'm going to talk about the sun, which is what I do in my research group. I try to understand the basic physics of the sun, and I'd like to tell you the story of the kind of research that we do here in the research group. So we have a large astrophysics research group in Trinity. We have grown over the past 5 or 6 years, and we now have an active group of students, postdoctoral research fellows, and academic staff working on the sun, working on stellar physics, and engaged in both research and teaching, and a lot of outreach as well. So today, though, I'm going to talk about one particular aspect of that, and that is the sun, and that's solar physics and how the sun affects us here on Earth. So this is what we all have in our mind when we think about the sun, a big ball, pretty much featureless up in the sky, but from time to time you see small dark patches appearing on the surface of the sun, and these are called sunspots. So you can see these bright sunspots. This is what Galileo first saw when he trained his telescope onto the sun in the early 1600s. And it's inside these huge areas of magnetic field that you get explosions happening called solar flares. And it's these solar flares and it's the sunspots that I'm particularly interested in trying to understand. And just to give you an idea of size, the Earth is probably the size of that one that's just decaying there. So these larger sunspots that appear, these ones are many times the size of the Earth, to give you an idea of how large these aspects are. Now, once you go above the Earth's atmosphere on board a spacecraft and you put an X-ray imager or an extreme ultraviolet imager on board them, then the atmosphere changes dramatically and the sun looks more like this. So this is the solar corona as seen with a NASA spacecraft called the Solar Dynamics Observatory. And what you can see is that the atmosphere is, it's full of hot gas. This is 2 million degree Kelvin, 2 megakelvin gas in the sun's outer atmosphere. And we're still not really sure why it's so hot. One of the big questions in contemporary physics, well, maybe not just contemporary physics, but the past 100 years in physics is why the corona is 2 million degrees Kelvin, because the surface is only 6,000 degrees Kelvin. How come when you move away from a hot body does the temperature go up? There's a problem there. But anyway, that's an active research topic. But also what you can see up here is a huge explosion. This is a solar flare going off. So over a time scale of about 10 minutes, you get a huge amount of energy being released. 10 to the 27 joules of energy are released over a matter of minutes. And sometimes the hot gas, the plasma that's heated in there, can escape the gravitational field of the sun. And if it does, it can come flying towards us or towards other planets in space. One thing that we would like to be able to do is when we see one of these explosions going off on the sun, we want to make an estimate of when it's going to hit us here on the planet Earth. So that's one of the active areas of research that my group are interested in. Once you move away from the surface of the sun, then you can see the outer atmosphere. And so what you're seeing here, here's the lower atmosphere of the sun here. Then what we have is, these are a series of what are called coronagraph images. So here's the inner portion or close to the sun. Now we have another camera that gets you out to about 32 times the radius of the sun. Well, this one doesn't, but some of the other cameras do. But what's important here is to note that there's an explosion that happens in the sun, a flare, and associated with that is an ejection of hot plasma into space, and that's called a coronal mass ejection, or a CME. And once these CMEs move through space, they carry with them gas, hot gas, so millions of degrees Kelvin, and they carry magnetic field with them. And when these storms come through space, they can have impacts, a variety of different impacts on the planets as they move through space. The speeds that these are moving at are hundreds of kilometers a second. So if they're traveling at hundreds of kilometers a second, they can get to Earth in 3 to 4 days. But if they're traveling at, sometimes they can travel at up to 3,000 kilometers per second. And if they travel at that speed, they can get to us within about a day. So 17 hours is the fastest we've ever seen one of these solar storms get from the surface of the sun to the Earth. Okay, so they don't stop there. This is real data, by the way, before somebody asks. This is not a Hollywood animation. This is NASA stereo spacecraft data. Over here you have the sun. So this is the lower atmosphere of the sun. Over here the blue dot is us, sitting here in space. Then our next planet in, Venus. And what you can see is just this continuous outflow of gas, protons mainly, from the sun through space on its way to the Earth. But what you can also see is things like this, which are gusts in the solar wind, or coronal mass ejections. And what we'd like to really understand is what are the forces that govern the motion of these? You know, seems like a simple question. How do you drive these? Well, we still don't really understand how you drive coronal mass ejections through space. But with movies like this, which takes scientists many months to put together with different instruments, you can try and follow these coronal mass ejections through space and work out when they're going to hit. This is a unique data set, really. The stereo mission was launched, it's 2 spacecraft, launched in 2006, and they're giving us a perspective along the Sun-Earth line, but they're on their way to the other side of the sun at the moment. So once they go onto the far side of the sun, we won't see them again. That'll be the end of the mission. Once these solar storms then hit the Earth, they're confronted by a magnetic field. So we're very lucky that our planet has a nice strong magnetic field, but some of the particles can make their way into our magnetosphere, our protective magnetosphere. And when they do, they can sometimes make it right down to about 50 kilometers above the surface of our planet. So these particles are making it 150 million kilometers from the surface of the sun almost to the surface of our planet. And in some cases, those particles do make it down and you get what's called a ground level event. So you do sometimes get particles coming the whole way down. But the Aurora borealis, the northern lights that you see here, comes from particles from the solar wind or from coronal mass ejections, making it through the Earth's magnetosphere and producing these spectacular reds and greens that you see in the Earth's atmosphere. So to create the Aurora borealis. Here's a beautiful picture taken last year showing an aurora. This was in, I think, Michigan, in the northern portions of the US. So you can see these beautiful greens coming from about 50 kilometers up. There's a slight red hue here, which you can't see very well. It also can be seen from here, from Ireland. Here's from County Donegal. This was looking north from the Inishowen Peninsula. This was actually the front page of the Irish Times. And you can see a particularly strong glow here, which came from a solar storm that left the surface of the sun about 2 days previous to when this picture was taken. So these solar storms and their effects can be seen right here on Ireland. And it's not always beautiful, the effects that they can have. They have these spectacular effects that you can see in our ionosphere, but they can also have effects on the technologies on which we all depend so much on an everyday basis. One of the first things that are affected by solar storms are satellite electronics. So if you have a satellite sitting up there and a portion of your satellite becomes charged, then you'll get a potential difference across your spacecraft. And the last thing you want is a potential difference running across your spacecraft, because then nature doesn't like potential differences. It tries to get rid of them. And what it does is it causes a flow of current through your spacecraft, and that can burn out sensitive electronics on board spacecraft. One thing is that the people like Motorola and the telecoms companies won't tell you this. The last thing that they want to do is tell you that their assets are vulnerable to space weather effects. So they don't like talking about it. And the other people who don't like talking about it are the military as well. They were the people who invented GPS, and they also don't like to tell you about the effects on space weather. But what is very telling is the fact that big insurance companies are very interested in looking at how much these space weather effects are going to cost, because they're the ones who are insuring some of these assets that are in space. So people like Swiss Re and Zurich are very interested in the effects of space weather on satellite hardware. The next thing that we all depend on, if you have a mobile phone in your pocket, well, a good mobile phone in your pocket, you probably will have GPS in your phone. So we all depend on GPS. It's in our phones, it's in our cars, it's part of our life. And that GPS signal that we all rely on is affected by space weather. So the GPS signals come through the Earth's ionosphere, and if the ionosphere is perturbed by a solar flare, it can cause errors in GPS. So you don't know where you are, and the accuracy can fail by up to 10 meters. And 10 meters is a large distance if you're drilling somewhere. If you're using GPS, say, to drill for oil, and you're out by 10 meters, that can make a big effect. If you're trying to surveying for a building and you're out by 10 meters, that can be a big effect. So the effects on GPS can be quite pronounced. The last thing I'll mention really is the effect on the power grid. In 1989, in Hydro-Quebec, a huge solar flare, actually it wasn't a huge solar flare, a pretty average solar flare, knocked out the power grid in a portion of Canada, leaving 6 million people without power for 9 hours. So it was a huge effect, and it was a cold March evening when they lost power in Canada. And it's not just because they have long conductors in Canada. You can also get currents induced in the surface of the Earth, and then they can jump up. You can get currents induced in the sea, and then it can jump up from the sea up into the land. So even a small country like Ireland can have a risk to these geomagnetically induced currents that are driven by solar storms. So in Scotland, for example, they constantly monitor the effects of solar storms on the power grid, and the same in England as well. In Ireland, we're now beginning to work with EirGrid to look at the effects of geomagnetically induced currents from space weather. So there's some applied astrophysics working here in Ireland, so that should keep the funding bodies happy. Okay, so how do we study the sun? One of the things that we do is we look at the radio emission that comes from the sun. The sun glows at optical wavelengths, it glows at X-ray wavelengths, but it also glows at radio wavelengths as well. And in order to observe the sun at radio wavelengths, we need to use radio telescopes. And this is a pretty spectacular looking array of radio telescopes in Nobiyama in Japan. And this observes the sun at gigahertz frequencies, so they're microwave frequencies. And you can use these to track the sun all day, and then you can make beautiful images of the radio sun. So this is a picture or a movie here taken of the sun's atmosphere at microwave frequencies. So this is at 17 gigahertz. So these are centimeter kind of waves. But what it shows you is the sun rotating, but you also have areas where there's intense heating above sunspots, but you also have a solar flare that goes off here on the left-hand side of the sun. At radio waves. And those radio bursts can cause effects here on Earth. They can cause dropouts in mobile phone coverage. They can cause shortwave radio dropouts as well. So that's at very high frequencies, at 17 gigahertz right up to 30 gigahertz and more. But you can also look at the low frequency sun as well. And this is a radio heliograph in Nancy, south of Paris in France. And this is constantly observing low frequency radio emission from the sun. So if you think about RTE, if you think about your radio, it's 88 to 110, I think it is, megahertz is where you tune into your radio. The sun also glows at those frequencies. And this picture here is taken at 164 megahertz. And this shows one of these solar storms going off close to where your dial is on your radio. But the sun glows the whole way from about 10 megahertz well, we can see it from Earth from about 10 megahertz right up to hundreds of megahertz and up to gigahertz. So the sun is a huge emitter of radiation. And that was first detected really in the Second World War when the British were looking for enemy aircraft coming across using radar. They noticed crackling in their signals, and they noticed that when they pointed their detectors or their antennas towards the sun, they were able to pick up the signature of the sun. So how does the sun create these radio waves? There's a variety of different things. First of all, the sun is a black body, and so it has a peak at 550 nanometers, but there's a big long tail in the black body, and the black body then glows also at radio wavelengths. So the quiet sun is what we call free emission, so that's black body emission. Sunspots have intense magnetic fields in them, and because they have intense magnetic fields in them, electrons like to spiral along those magnetic fields. And as the electrons move along the magnetic fields, they emit radio waves. So that's another way that the sun can also emit radio waves. During a big burst of radiation during a solar flare, you can cause instabilities in the gas, and that produces what's called plasma emission. So if you think about lots of protons sitting like that, electrons sitting like that, and they oscillate back and forth, and they emit electromagnetic waves, and that's called plasma emission. So there's lots of different ways by which the sun can emit radiation, depending on whether the quiet atmosphere or above sunspots or flares. So radio is very powerful at diagnosing the basic physics of what's going on the sun. So what's that got to do with sheep in Birr? So this is Birr, County Offaly in July 2010, and the Earl of Ross kindly donated us this beautiful sheep shed. And in the sheep shed, I opened the door and there were 3 sheep sitting in the corner of the sheep shed. And this was to become our future control room for Trinity's radio observatory in Birr Castle. So Birr Castle, as you are aware, is a very unique place in the history of international astronomy. In the 1800s, the Chancellor of Trinity, who was the 3rd Earl of Ross, built a 6-foot diameter telescope in Birr Castle. It was the biggest telescope in the world. It was the Hubble Space Telescope of its time, really. From the 1940s right up, or the 1840s right up until 1920, when the Hooker telescope was built in California. So the biggest telescope in the world was at sea level in Ireland. So there's a great tradition or a great heritage of astronomy. But also, it's very radio quiet. It sits in the middle of the country, away from Galway, from Dublin and Galway and Cork. And so that it's a very radio quiet environment. It's a great place to do radio quiet, or sensitive radio measurements. And it means that we can see very faint radio emission because we're not overwhelmed by artificial radiation from communications and the like. So we got a little bit of funding from our very kind head of school, and we started refurbishing the sheep shed control room. As you can see here, we pulled in cables, brought in power, brought in electricity, spent a lot of cold and wet days drilling through walls, putting cables in, and eventually we replaced the sheep with graduate students and got the room all done up. 2 guys are very happy here, and set up some antennas. Here's one of our antennas here. This is about 3 meters long, and it tracks the sun all day, every day, and the data goes into our control room here, and then that gets put onto the web. And we're now writing 2 papers that are going to go into the international literature that say we observed the sun from Birr, County Offaly, and blah, 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 blah. So I'm very proud of that we were able to actually do some good science from the sheep shed control room that will go into the international literature. These are the kind of data that we get. So this here shows time, and this here shows frequency. This data up here is taken by NASA's STEREO spacecraft here. It shows a burst of radiation at below megahertz traveling through space. And then this one here is the Ross Solar Terrestrial Observatory data that we take. But this here is connecting the whole way to the Earth. And what we do is we provide the last link to the surface of the sun. So it's a key part of the story, is telling you about radio bursts, where they happen in the sun's atmosphere. And you wouldn't be able to do it without the Ross Solar Terrestrial Observatory. And this thing here cost 20 grand. This thing here cost 500 million. So there's a little bit of a difference, but we're still able to combine the two data sources and try and do some new and interesting observations. When you zoom in on this, we have a lot of detail in our spectra as well. You can see that there's lots of just little tiny streaks in our data, and each one of those streaks corresponds to an electron traveling along a magnetic field emitting a frequency. And we can tell about electron acceleration from these data. So it's quite a rich data set, and we'll keep my two graduate studies up late, I hope, and up at the weekend, and up over Christmas, and up over Easter, working to get some of the data. But we believe that the data should be free. It's taxpayers' money. I think the data should go out there. And so all of our data goes online, and it's free. So anybody can download our data, anybody can use our data. We provide software for people to use our data as well. And if you can go to rossobservatory.ie, you can have a look at some of the data and have a look at the software. 5 minutes? 2 minutes? 2.5. 2.5. We're negotiating. Give you 3. All right. So all of our data goes onto the Ross Observatory website where you can download. And there are other international scientists who are using our data already. So we're going to see that appear in other papers. But that's where we are now. Where do we want to go? In many ways, that's just a start. That's almost undergraduate level physics. What we want to do is we want to build a LOFAR telescope in Ireland. This is what a LOFAR array looks like. This is in Holland. These are actually antennas underneath tarpaulin. And what they're doing is they're picking up radio waves from all around the sky. And what we want to do in my group is study the sun using these. And we want to build one of these LOFAR stations here in Ireland. So this is what an international LOFAR station looks like. This is one in the UK. This is about 100 meters long here. This is about 50 meters long. These guys here, these are all antennas, and they pick up radio waves from the sun, or from the stars, or from the early universe, or from exoplanets, who knows. And these ones here are the high frequency antennas. So they go from about 10 to 90 megahertz, and they go from about 120 to about 240 megahertz. And all the data from all of these gets piped back to Holland. So all the data from the UK, from Sweden, from Germany, from France, soon from Poland, are all going to go back to a supercomputer here in the Netherlands. And I'd like to extend that out here. Well, not just me. Almost every astronomer in Ireland would like to see that extended right out to the west. And the key thing about extending it, making a bigger footprint, is the farther apart you put these antennas, the finer the detail you can see on the sky. So there's a good technical reason for putting an antenna here in Ireland. This is a close-up on some of these antennas. Here's the wires on them. They're all connected by cable under the ground back to the main control center. Here's the other antennas. Here's one of my postdocs and one of my students with two of our German collaborators looking at these and looking extremely cold. And then this is inside the control room. So all of the data from these goes into these computers, and they come out via fiber optics at the far side. And then once on fiber, they go on 10 gigabit fiber, very fast fiber. They go out back to Holland. So where are we now? We need 1.5 million. That's where we are. The network cost 150 million. So you do the math, you can see the benefit there. If we get 1.5 million, we can get into a 150 million network. How much do we have? We've got about 10% so far. So Dermot Desmond thinks it's a good idea. He's apparently quite a smart guy. Dennis O'Brien, I'll say nothing more. He's given us a little bit of money as well. But we want to make this project happen over the next number of years and try and give this guy some kind of future in science. All right, so thank you very much for your time.